Okay, this is going to be a short video addressing the physics problem of projectile motion. This came up the other day in an A-level physics course I was tutoring, and a more difficult version of this, which we'll talk about, came up in a Facebook help group. So we're going to address the problem two ways. First of all, the simple case that came up in the A-level course, and typically in the US, this would be grade 11 physics, first physics, and maybe in the university physics for non-STEM people. And there's a formula. So we're just going to solve the problem using a formula first. But that's not very general, and we can't solve more complicated problems that way. So we're going to solve the same problem the second time using the equations of motion. And that's more general. We can solve more interesting problems that way. That would be the way you would be expected to solve it in a STEM physics course using the equations of motion. And then at the end, we'll take a look at this on Desmos. They actually have a built-in projectile page, and you can see what happens when you change some of these parameters. So the basic projectile problem is that you fire something over here, and it lands over here, but you can't go in a straight line. Your arrow or your projectile isn't going in a straight line because of gravity. So you need to fire it upwards like this at some angle. So my initial velocity is at some angle called theta. So I fire it with an initial velocity at some angle theta, and gravity causes it to arch and hopefully land at the same height at some distance. So this is called the William Tell problem because William Tell disobeyed the king. He didn't bow down to the king's hat. And as his retaliation for that, the king made William Tell fire an arrow, and it had to hit an apple on the top of his son's head. So he has to fire this arrow at some angle. If he fires it in a straight line, it's going to just fall down and probably hit his son too low and kill his son. So we need to figure out what angle William Tell needs to fire this at. Then there was another person who could have benefited from this, William Burroughs. He was using a gun, so this angle would be much, much smaller. I'm not sure a calculation would have helped Burroughs much. So we have, in the William Tell case, we have a distance of 25 meters. This is how far away the sun is from William Tell with his bow and arrow. And we know that he fires it at 45 meters per second. That's the speed that the arrow leaves the bow with. And we want to find this angle. So the easy way is that we have a formula for range is equal to initial velocity squared times sine 2 theta over g. And g is the acceleration of gravity that's pulling this downward. That's 9.8. So we can just solve this. We know what r is. R is 25. That's the range or the distance it travels. We know the initial speed, which is 45. And we know g. So we just solve this for sine of 2 theta. Sine of 2 theta is equal to r g over the initial squared. We plug in those numbers, and we get that theta is approximately 3.46, depending how you round. So that's the angle that William Tell needs to fire his arrow at. So that's the easy way of solving projectile problems, but it only works if your landing point is at the same height as your starting point. So we have a couple other cases where that might not be true. The problem that was posted and I'm currently helping someone with on the Facebook group is that there's a rocket motor. So this is, I'm not going to do this problem today, but it accelerates with the booster rocket up to here. So this isn't part of the projectile motion. This just is a straight line motion, and you have to figure out up here what the initial is. But the range then is over here. So my projectile part of this problem has a higher starting point and a lower ending point. And this formula doesn't work in that kind of case. We're also making an assumption here about William Tell. We're assuming that the apple on his son's head is the same height as the arrow. His son is shorter, according to the accounts I've seen. He has a small son. On the other hand, the arrow isn't at William Tell's head height either. So if the arrow height is at about the same as the kid's head, then this is a good assumption. So in physics, we're always making assumptions. It's a good idea to try to recognize those and figure out what they are. Sometimes there's so many we don't think about it. So the kind of the unmentioned assumption here is that the apple on the head is the same height as the arrow. And that allows us to use the formula. So the more general way, but the other thing to mention is that when people get help on Facebook groups and places like that, and somebody posted this problem, and immediately some teacher, tutor in the group posted a bunch of equations, including this one and a couple others for velocity or something at the high point, which we can calculate. And so their only approach to problems at all is to come up with a formula. So someone posts a question like this and they say, oh, here's a bunch of formulas you can use. Well, those formulas don't work. You need to go back in those problems to the original equations of motion that we learned in kinematics. So let's write down these equations, and we're going to do the same problem, the simple one, but we're going to do it using the equations from the beginning rather than formula. Acceleration. So we have some known acceleration. In this case, it's simply g. We have velocity, which is acceleration times the time, how fast you're speeding up times how long you speed up. And we also have some initial velocity that we start out with. And then we have s for distance. So s is how far it has traveled in any particular time. It's called displacement, but for some reason we use s. According to where you look up the lexicon history of this, it's either of German or Latin origin, but it's common to use s. And now we have 1/2 a e squared plus b initial times t, plus we may have some starting position s. And if you've had basic calculus, you'll notice that this is the derivative of s, and a is the derivative of v with respect to time. So these are actually intimately related graphically and through calculus. And that allows us to do even harder problems than we'll talk about today. So we're just going to use these. We're not going to use any calculus today. The other thing about these equations is that there's a bar on top of many of these quantities. That denotes a vector quantity. So the velocity has a direction. We know up here, all we needed in the equation was a speed. We just needed to know how fast it went, 45. And then the angle came into the equation here. But when we work with a vector, we need to work with the two parts of the vector, the x part and the y part. So acceleration has two components, left and right, up and down. In this case, it's just going to be minus g in the y direction. Here we're going to have two components. We have a velocity in the x direction, and we have an up and down velocity. We have a distance traveled this way, and over time we know how far the distance is up and down. So rather than use the whiteboard for calculations, I'm going to go over to the document scanner. That is a better tool for this, and we'll solve these equations, which isn't that hard. And then after that, we'll go look at Desmos and actually look at this projectile, this trajectory of the projectile. Okay, so here we are at the document scanner. For reference, you can still look back at the whiteboard over there. So you can see our equations over there, acceleration, velocity, and distance. But we need to write these in the x direction and in the y direction. So we have an x acceleration, and there's no bar. Now I'm dealing with only the size of the acceleration in this direction. So this is 0. There's nothing speeding up or slowing down the arrow in the left-right x direction. And I have v x, the velocity in x direction, and that is my initial velocity, which is vi, but I need the x part of it. So that's cosine of the angle we fire it at. This is v initial x. And we have to add a t. And there's no acceleration, so we don't need that term. And then we get to the distance traveled in the x direction. And here we have, we're going to assume the initial position, s initial is 0. So we're going to call the starting point over here. This point is going to be 0, 0, 0x and 0y. And I have my initial x position, which is vi cosine theta. That's my initial speed in the x direction times time. So these are my x equations. Now I need the y part of my vectors. And the acceleration in the y direction is minus g, which is minus 9.8. And my y velocity is my initial y velocity, which is vi times sine theta. And then I have to add gt, so minus gt. So this is my equation for velocity in the y direction. And I have my y distance, so I'm going to have my okay, so here are the equations that I can use to solve this problem. I have my x equations and I have my y equations. I have two things I don't know, which are theta and time, but I have a bunch of equations. So if I can find two independent equations, I can find two variables. And the one I want to find is theta. I want to know what angle he fired this at. So what I'm doing up here with the sines and cosines is that this is a cosine of theta times the side of the triangle, and the vertical part is sine theta times the length of the hypotenuse. So that's just trigonometry, and we use that when we're working with vectors. So now I just have to solve these. So let's look at, and you can do this in a number of ways. You can start with this equation over here. I'm going to start with this one. And I know that the y position of the height is 0 at the end. So let's set this equal to 0. And this is, vi is 45 sine theta times t. Minus 1/2 g, that's, let's just call that 5. Let's call that, for now, g over 2, t squared. And this is equal to 0. And I can solve this for t in terms of theta. First of all, there's a t here, and there's 2 t's in this term. So I get t times 45 sine theta minus gt over 2. And so I have two solutions to this. T can equal 0. And that's the obvious trivial solution. We know that. When time is 0, the y position is 0. It hasn't yet gone anywhere. So what I'm interested in is this part, and I have to set this equal to 0. And this is the second point where it hits the apple. So 45 sine theta has to equal gt over 2. And now I can solve this for t. So I get t is equal to 2 times 45 times sine theta over g. I can plug this time into the other x equation. And this isn't 0, this is 25. Okay, when it hits the apple, that's 25 meters away. So now for that one, I have 25 is equal to vi, which is 45, cosine theta, which is cosine theta, times t, which is 2 times 45 times sine theta over g. Okay, so now I can solve this equation for theta. So I'm going to get, let's rewrite this. I get 2 times 45 squared times cosine theta sine theta, and have a g down here, right? So if I use my trig identity, slide this paper up again. Cosine theta times sine theta is equal to sine 2 theta. So this equation just says that 25 is equal to 2 times 45 squared. Actually, it's 2 times that. Sine 2 theta over g. Now, if you look back at the board at the range equation, that's actually what we have. This is r, this is the range. This is the initial velocity squared. This is sine 2 theta, and it's all over g. So I really ended up with the same thing because the problem is a simple problem. In fact, that range equation r is just derived from these equations. Many textbooks will just do that in general on a problem entirely with variables. We sort of did that here, but we did put in some numbers for our variables. Now if we put in g is 9.8 and solve for theta, we get about the same thing, 3.45. So this is a nicer, more rigorous way of doing it. The range equation is a nice shortcut. It's convenient if you just need an answer, but it doesn't really serve general purpose, and it also doesn't really provide any insight into the kinematics of the problem. If we had something like the rocket problem, we have a starting height. So Sy up here is going to have, in this case, there's going to be some initial y position, Sy initial. You're going to have a starting point. Sx is not necessarily 0, although in the rocket problem you're going to have to add some x distance. So you can solve it using this. You're not going to end up with something quite as simple as the range equation. The algebra will be a little bit different, but you can solve all kinds of problems when you begin with the kinematics equation. So now we found out that he needs to go at an angle of 3.45. Let's go to Desmos here and have a look at this. In Desmos, and this is just built in, I didn't construct this page, you can change A, which is the angle. So 3.4547 is our angle. Velocity is 45 degrees, and we fired it from a height of 0. And over here you can see that the final ending point is pretty close to 25. There's going to be some rounding. I thought I had it around 25, but it's going to depend on some rounding in your calculations. We can see in this case what will happen. So what happens if I do fire it from a higher height? Well, if he fires it from too high, 25 meters is about here. And there is going to be too high. It's going to go over the kid's head. It's not going to hit the apple. So I can change this height and then play around with this. The standard problems is just, I could start below 0, but I eliminated that. So, but there's no reason you couldn't start below 0. We could change the velocity. So if we reduce the velocity, it's not going to go as far. It's going to fall short of the sun. We could increase it, but it's cut off right now at 25. You could change that. Then we have the angle. So if he fires it at too high an angle, it's going to go over this kid's head. We kind of expect that, wouldn't we? And if he fires it at a 0 angle, or very close to 0, it's not going to go very far. It's going to hit the ground after 2 meters here. So we need to So one question that arises is how do you get the maximum range on a projectile? We have to zoom out for this because we're only at 3 degrees. If we have Burroughs using a gun, we'd have even less than 3 degrees because the initial velocity, muzzle velocity, would be very high. So we go to the angle, and if we fire it at a higher and higher angle, it goes further, right? And we're going to have to zoom out even further because there's a big difference between 3 degrees and 25 degrees or more. And right here, you're going to see it, the range starts to shorten again. And this makes sense because if we fired at an angle of 90 degrees, which is straight up and down, it's going to come straight down on our own head. And that's either the wrong apple or I don't have an apple on my head. So the maximum range is going to end up being at 45 degrees. And this is another thing that's very easy to show with calculus. You take that range equation and take the derivative to find the maximum, you'll find it's 45 degrees. So that's the Desmos version. Let's wrap up what we did here. And so what we talked about was the basic William Tell problem, which is a simple range problem, and it's conducive to just using a formula. So we have this formula, we plugged in the numbers, we got the range, and that's all fine for that kind of a problem. It lacks any rigor or insight, but it gives you the answer. And in the earliest courses, that's really what they're asking you for the answer. Then we went back and we used a more general approach, and I'm going to get rid of the minus J. We didn't talk about the J unit vectors here. So A is just a constant acceleration, and that's going to be true in the vast majority of problems, even through STEM physics. We don't include a lot of varying acceleration problems because they get more difficult. We do expect those students to know calculus, but the problems are still beyond the course for the most part. We have velocity equation and a distance equation, and we have an x part and a y part. And we would have a z part in some cases too if we work in 3 dimensions. This was a little bit harder. We had to do a little bit of math. We had to write down the x equations and the y equations. And we had to choose 2 equations to find data and time. We didn't finish finding time because you don't need to. You can go back and do that and verify the solution. But one reason we did it this way was to be able to account for a starting point up here. So if I start with an initial y distance, and actually there's an initial x distance here too, what I kind of mentioned and glossed over the document scanner. We're starting our projectile problem here, and we're starting at a certain height. We're also starting at some x over here because the rocket thruster, the booster thrust started back here. And we can do that kind of problem. And if you do it with these equations, it's not all that much harder than the simple problem. A little bit more algebra in the computation, but it's so you can start all kinematics problems from these equations and solve a lot more things. And then we looked at this with Desmos. Desmos is a great tool. I encourage people to use some tools like that to give you insight. They are not tools that give you an answer. Okay, I saw a student in one program that used symbol lab for derivatives, and he had no idea at all how to take the simplest derivative. Yeah, because he just only knew how to plug it into symbol lab. Yeah, I just don't recommend doing that because it will catch up with you at some point. But tools like Desmos are actually very good. They give you some insight. We solved the problem first, and we wanted to have some insight without doing a lot more calculations for different scenarios. We could vary h, it could vary v, and it gives us a little insight into what exactly happens with the projectile. So there's a lot of different tools like that. Desmos is a particularly good one, and it's good for getting some insight into the problem. So that's the William Tell problem. William Tell, William Burroughs, either one. Probably better, more amenable to William Tell. And it's a simple projectile problem. And it's a real problem that comes up in courses, okay? Because this simple version just came up in an A-level course. All they did was want you to plug numbers into here and give an answer. And that's all they did with it. And maybe all they did with projectiles at all, I'm not sure. Then you can also do it this way, and this was necessary for the rocket problem, which is another textbook problem that came up on Facebook. So this problem that requires this is probably from a second course, a university course. But these are real courses, and the rocket problem is a real, potentially simplistic real life problem. Okay, I worked with rocket motors for a while. There's a thrust from the booster, and you go in a straight line, and then you have a projectile. So these aren't abstract, useless problems. William Tell's a little historical, perhaps, but these are real-life problems, and I hope this will help you solve such problems in your physics courses. So that's it. Good luck in your physics. I do offer tutoring and teaching. If you need more help with this, I'm available for individual meetings or for ongoing sessions, and I'm in the process of putting together some actual courses. Contact me if you want to pursue any of this further, or if you just have any particular question. Many times, short, simple questions, or a special short question about this, I'll answer just for free. You don't need to pay me for tutoring for very simple things. And I'm also helping on several Facebook groups. When the problem is interesting and the student is asking a question, I provide some free help there also. I just don't help the people that post their entire homework assignment and not the answers. Okay, bye.